This slide presents a sample of force versus deflection graph. This sample is a deflection test on varying lengths. Each trend line on this graph represents forces, which were placed on the bars by hanging different masses from them, and the corresponding deflections. Each trend line consists of one length. 6 different lengths were tested with 3 different forces and deflections, thus producing the 6 trend lines. Each trend line slope represents the stiffness of the bar with a specific length. Material, thickness, and width were the same for all 6 different length testings. Therefore, length was the only varying factor between these trend lines. Since we knew the stiffnesses of bars with varying lengths, we could plot these points on a stiffness versus length graph and fit a power trend line to this data. Using polyfit, we derived an equation for this trend line. This equation revealed the exponent on the length to be -3. We carried out the same process as described on the previous slide and this one to find the exponents for width, material, and thickness as well. Once these exponents were known, the value for the constant was the only variable left to solve for.
Once the exponents for elastic modulus, width, length, and thickness were found using the polyfit, the equation became stiffness K equals the constant C times elastic modulus E raised to the first power times width W raised to the first power times thickness T raised to the third power times length L raised to the -3rd power, as shown by the equation in the first box. By manipulating the equation shown in the first box, it was then possible to solve for the constant C. This manipulation is shown in the second box. The constant C was calculated using deflection data taken from the laboratory. Because each deflection had a different stiffness depending on the parameter change, each deflection would also have a different calculated C value. The eventual result of this was the calculation of 21 different C values, one for each deflection performed. Although the C values were different for each deflection, the difference was not extremely significant. For this reason, an average C value was computed using the 21 different C values previously calculated. The average C value was 0.1904, which was rounded to 0.2 in the final equation. The results of the polyfit data and the C value calculations are shown in the table. The final resulting equation is shown in the third box. This completed equation would then be used to mathematically predict load or deflection based on beam properties.
This table shows data from the beams we tested for the load on a beam. As you can see, the first beam we tested was 15 inches long, 2.5 inches wide, and 1/8 of an inch thick. We were looking for a deflection of 1 inch. After running these numbers in our code, we found a predicted load of 1,312.5 grams, or 1.31 kilograms. After testing the actual beam in the lab, the beam deflected 1 inch, with a load of 1,374 grams. This gave a great result of 4.4% error. The second beam tested had the parameters of 17 inches long, 1 inch wide, and again 1/8 of an inch thick. We were again looking for 1 inch deflection, and our MATLAB code gave us a load of 360.6 grams. After testing the beam in the lab, we found it deflected at a load of 367 grams, giving a terrific percent error of 1.7%. This second data table shows data from our deflection testing. In this test, we applied a specific load to the beam and calculated an expected deflection result. The first beam we tested was 15.5 inches long, 2 inches wide, and 1/8 of an inch thick. When a load of 1,000 grams was applied, our MATLAB code gave a resulting deflection of 1.06 inches. When we tested this beam in the lab, the beam actually deflected 1.22 inches. This gave a percent error of 13.1%. The second beam we tested had the parameters of 13.5 inches long, 1.25 inches wide, and again 1/8 of an inch thick. Again, applying a load of 1,000 grams, the MATLAB code calculated a deflection of 1.1 inches. This was very similar to the actual deflection when we tested the beam in the lab, which was 1.13 inches, giving another great percent error of 2.65%.
Once we have developed and tested a working model, the next thing we want to do is take that model and apply it to a real-world situation. Engineers Without Borders is constructing a mechanism that's going to support several analytical devices to measure the water quality of a jungle stream. And one of the things we want to look at is, based off the drag weight of these analytical devices and the force it applies to the beam, how can we make a proper selection as to what sort of beam that support should be made out of. So the two main things we want to look at are, okay, how can we configure these beams to minimize forces for a 1-inch deflection, as well as how can we do this as economically as possible. There are 6 available beams for this project, each with different parameters for length, width, thickness, and material. What we want to do is apply these dimensions into our program and solve out to figure out how much load it takes to apply to a 1-inch deflection. We can call this the maximum load, which in other words is the maximum amount of force we can apply to a beam without it exceeding our maximum deflection of 1 inch. Although we had calculated our loads from the maximum loads from the previous slide, what we can also do is account for a secondary loading scenario that we can use to our advantage. In this, we take each bar and we turn it 90 degrees in its mounting mechanism. In doing so, the width effectively becomes the thickness, and the thickness effectively becomes the width. Since stiffness is proportional to the cube of thickness, then when we orient the beam to have the largest possible thickness, we're more resistant to deflection and can get more load without achieving our maximum deflection of 1 inch. If we rerun each of these bars through our program to evaluate the maximum load once more, we're going to see a significant increase for all of the beams in which the effective thickness is increased. Notice that there are 2 bars where this does not change, and those are because the thickness and the width are equal. But for each of these where we actually ended up increasing a thickness, we ended up with a more significant max load and hence can put more drag force on those beams. Once we've accounted for the maximum loadings for all 6 bars at the 2 possible orientations, we can then take advantage of the additive nature of drag force and essentially assign each device to a beam. And when we add up the drag forces, we have to make sure that we stay underneath the maximum load. As long as we stay underneath the maximum load, when we go through and calculate the deflection, it will be under our target of 1 inch. After some experimentation as far as assigning analytical devices to beams, there emerges a fairly straightforward solution as far as our most cost-effective method of mounting these devices. Beam 1, if we mount the velocity flow meter, turbidity meter, and portable sampler, we encounter a total drag force of approximately 8 pounds, which once we run through our program, we determine that gives a deflection of 0.6 inches, which is well underneath our target. In addition, since we can only mount up to 3 devices on a single beam, we have to employ a second beam, which we chose to be beam 6, on which we will mount the nutrient meter and the pH electrode, which generates a total force of about 2.5 pounds force and a deflection of 1/2 inch. Again, that's approximately half of our target. We chose these 2 beams because they are the 2 cheapest, but however, it does bear mentioning that there was the $4 beam, which was significantly cheaper. However, with the force we calculated, it would not handle the load of any of these devices. So effectively, we chose the 2 cheapest beams that would support the drag weight that we needed to support.